All right, today we're going to talk about bases. But before we begin our discussion of bases, I do want to finish up one last topic in our discussion of acids, which is going to be how we calculate our acid dissociation constant Ka for a weak acid. Now let's say that we have a concentration of some acid that we know is weak at the very beginning, so our initial concentration happens to be 0.185 molar, and we also have the pH, right? Well, what we're going to do is we're going to set up an ice table to calculate our Ka. The first thing is set up ice table. All right, so we're going to write our reaction. We have HA plus some water, right? Because we can include our water in our dissociation reaction. And if we do, right, then we know that we're going to have H3O plus A minus. This is just another way. You could leave out the waters, okay? But if you're setting up your ice table, and you've included the water in your reaction, okay, then all you have to do is put a column for each of your species except the water. So I usually just draw the whole table and then I put a big X over my water. I still need to keep my hydronium because that contains the H plus that I'm going to need, okay? Now, then I'm going to put in my initial concentration, 0.185 molar. These are 0 because I started out with none of those. There's nothing in the problem statement to let me think that there might be. All right. Then I go 1 times negative X, 1 times positive X, and 1 times positive X. Remember, I always want you to show your stoichiometric coefficient and the change because these stoichiometric coefficients may not always be 1. All right. So then we have the addition of these. So we've got 0.185 minus X. We have X, and we have X. Then what we're going to do is we're going to write our Ka. So we have Ka is equal to X squared over 0.185 minus X. And that's equal to, we would have to look up our Ka in a table, right? But we know that that is equal to our Ka. So say that we couldn't look it up in a table, and we're trying to find our Ka. We know that our Ka is equal to this, okay? So at this point, right, we need to figure out what X is. All right, the only other piece of information that we have is our pH, okay? So if you were working a problem like this on an exam or a quiz and I didn't give you the Ka, try to solve for your Ka using this information if it's being asked for in the problem statement. Our third step is going to be to calculate X. Now, the way that we're going to calculate X is that we know that our pH is equal to the negative log of our concentration in H plus, okay? Now, if you also remember, our concentration in H plus is equal to 10 times my negative pH, or 10 raised to the negative pH. So in this case, my concentration of H plus at equilibrium is equal to 10 to my negative pH, which is 2.95, which means that my concentration of H plus is equal to 1.122 times 10 to the negative 3 molar. Okay, so that's my concentration of H plus at equilibrium. Okay, now at this point, I then know, okay, my concentration of H plus, that's the same as my concentration of hydronium ion. Okay, so my H plus is equal to my concentration of hydronium, H3O plus at equilibrium. Okay, so now I know that this in my table, my X, right, my H3O plus at equilibrium, that was X, is also equal to my 10 or my 1.122 times 10 to the negative third. So then I plug in that value of X, so I have 1.122 times 10 to the negative third raised to the second all over 0.185 minus 1.2 or 1.122 times 10 to the negative third. Okay, and then I just solve for my Ka by calculating that value, and that gives me 6.85 times 10 to the negative 6. Okay, so that would be my Ka. Again, all I did was I said, okay, I need to calculate X to put into my Ka expression because I don't know what that is. Okay, one way to calculate X is to use what other information I have and solve for what I don't know, okay? So I'm going to calculate X by using my pH to get my concentration in H plus and then get X, okay? Because I know that my pH will give me my concentration of H plus, I can relate that to something in my equilibrium row, which is my H plus or H3O plus concentration. And then I just say that that is equal to whatever I found for my concentration and what was in the row, okay? And then I just evaluate that as my X into my Ka and solve, okay? Now, the next thing, I guess I don't want to erase this, the next thing I wanted to talk about is bases, okay? So if we are on slide 29, good thing I didn't erase that whole board, that would have been sad, all right? We know that we have multiple different types of bases, okay? We have Arrhenius bases, which produce OH minus, and we also had those Bronsted-Lowry bases, which accept H plus, okay? Now, like acids, when we're calculating, our strong acids are going to completely dissociate into ions, okay? And so they're going to have a Kb, or a base dissociation constant, which is greater than 1. So for example, if we were to look at an Arrhenius base, we have NaOH, and it's going to completely dissociate. So I've got one big arrow to the right, giving me sodium ions and hydroxide ions, right? Now weak bases, on the other hand, they're only going to partially dissociate. And they're going to have a Kb less than 1 because they aren't forming as many ions and they form in equilibrium, okay? In addition, because they're forming in equilibrium, we need to use an ice table for problems for weak bases, right? Now, if we were to look at something like a Bronsted-Lowry base, which accepts a proton, we could say, well, ammonia accepts a proton, becoming ammonium ion and hydroxide in solution. All right, so that would be an example of a Bronsted-Lowry base. There's going to be a list of acids and bases on slides 28 and 29. Please memorize those. All right. Also, many bases don't contain OH minus, as I was saying, right? Those would be your Bronsted-Lowry bases, okay? But are going to accept a proton. So we need to make sure that we keep that in mind as we're solving our various problems, okay? So let's do an example. So on slide 31, all right, we're going to do an example for a strong base, okay? And it says, what is the concentration of OH minus and the pH in a 0.25 molar KOH solution, okay? Well, it's actually saying what is the concentration of OH minus at equilibrium in a solution that we made or prepared that had an initial concentration of 0.250 molar, okay? So, as what we did for the strong acids, right, our very first question is it strong? Okay, well, is KOH a strong acid or strong base? It would be a strong base. Strong base. I guess I should have asked, is it a strong or a weak base, right? It's going to be a strong base. So if the answer is yes, then we're going to convert our concentration of our compound into our concentration of OH minus, okay? So we've got our concentration of OH minus. Let's see, And then we are going to use our chemical dissociation reaction, which is KOH goes to K plus and OH minus, right? The strong base, so it's going to completely dissociate. We know we have a 1 mole to 1 mole ratio, right? So we're going to take our concentration 0.250 molar potassium hydroxide, so which is moles per 1 liter, right? That's what molarity is. And then we know that for every 1 mole, using our stoichiometry of KOH, we put that on the bottom to cancel. For every 1 mole of KOH, we produce 1 mole of hydroxide ion. Okay? So that means that our concentration is going to be 0.250 molar hydroxide ion. Okay? So now that's going to be our concentration of OH minus. Right? It also asks us to calculate our pH. Now, if we're asked to calculate our pH, the first thing we need to calculate is our pOH, because that's a whole lot easier than going through the other way. So we're going to calculate our pOH, which is equal to the negative log base 10 of our concentration in OH minus. Okay, so we're first getting our pOH, and that's going to be equal to negative log of 0.205, which is equal to 0.602. Okay, then we're going to calculate our pH. And we remember that pH plus pOH is equal to 14, which means that my pH is equal to 14 minus pOH, which is equal to 14 minus 0.602, giving us 13.4 as our pH. Okay, so that would be my pH. My pH is very high, which means it's basic, and it should be since we're dealing with a base. All right, next, let's do an example of a weak base. All right, I wanted to give you an example using ammonia because that's going to be an example of a Bronsted-Lowry base, right, because it accepts a proton. So let's go to slide 32. All right, so weak base example. All right, here we're going to find our concentration of OH minus and the pH of a 0.250 molar solution of ammonia. Okay, notice that it's asking for our OH minus concentration, not our concentration of NH3. All right, now the first question is it strong? And the answer is no, it's a weak base. Okay, so if it's a weak base, that means we're going to need an ice table. All right, so let's set up our ice table. And the way that we do that is we write our dissociation reaction, which is NH3 plus OH, or plus H2O in equilibrium with NH4 plus and OH minus. Okay. And then ICE. And my pen is dying. Let me put in a new cartridge. While I'm doing that, what are going to be my initial concentrations in my table? Well, I know that I have my initial concentration of ammonia, which is 0.250 molar. okay? My water column, I'm going to cancel out because it's not going to participate, right? And then I have my NH4, my ammonium, 0 molar, and 0 molar for my hydroxide. We're going to assume that it started out all as NH3 because that's what we added to our solution, okay? And then it began to split up. So initially we had 0.250 molar. Our change is 1 times negative X, 1 times positive X, and 1 times positive X. Okay, so we'll have X and 0.25 minus X, right? Then we would write our KB, okay, because we're talking about bases. That's going to be equal to X squared over 0.25 minus X, okay? Now, I would look this up in a table, okay? So I know that my KB for ammonia happens to be 1.8 times 10 to the negative fifth, okay? Then I would solve for X. Okay? I find that X is equal to 0.00212, right? And when you're solving for X, you could do your 5% rule or your quadratic, right? I'm just skipping those steps because I want to save some time, and you already know how to do that. Okay, so we'd solve for X. Now notice, X, once we have that, is equal to something in the table, right? But I'm interested in finding out what my pH is and what my concentration of OH minus is. So let's look at our concentration of OH minus at equilibrium. That happens to be X. So I know that my concentration of OH minus, that's what I want to solve for, is equal to X, and X is equal to 0.0212 molar. Okay, so that's my concentration of OH minus. Now I want to find my pH, right? Well, the first thing that I'm going to do is I'm going to calculate my pOH. Okay, so with bases, you have to do this extra step where we calculate our pOH. That's the negative log of my concentration in OH minus, okay, which means that my pOH is equal to, let's see, 2.674. All right, make sure you check, plug in your numbers and see if you get the same thing. So that's my pOH. Then I'm going to calculate my pH by taking 14 minus my pOH, and that is going to give me 11.33. Okay, now notice that for our strong base, our pH was higher. Okay, it was closer to 14. That means that it's a stronger base, right? Our weaker base had a lower pH. Okay, so it was less basic. Okay, so that would be how you do a strong base or a weak base problem. They're just like what we did with the acids, but you do them with bases instead. Okay? Now, the next topic is a little bit complicated. Don't worry, I'll walk you through it. Okay? Now, our next topic on slide 33 is about something called polyprotic acids. Okay? So, polyprotic acids have more than one proton that they can dissociate. Okay? Now, polyprotic acids only dissociate one H plus at a time. Okay? So, let's say, well, and before that, okay, so let's say that we have something like H2SO4, right? If we consider that, right, it's going to lose one proton, so it's going to have a Ka for this first loss of a proton, where we get rid of one proton and it becomes HSO4 minus, okay? So this would be the first step where it got rid of its first proton. And then it'll get rid of the second one as HSO4 minus, losing a second one, and it's going to have a different dissociation constant when it becomes SO4 2 minus, okay? So if your acid has more than one proton, right, H2SO4 has 2 protons. If it has more than one proton, it is a polyprotic acid, okay? This in particular, since it has 2, is a diprotic acid. If it had 3, it would be a triprotic acid, okay? And so on. But they're only going to get rid of one proton at a time, and each time they lose a proton, it has a different acid dissociation constant, okay? The first process is usually strong, all right? So your first dissociation is usually strong. Excuse me. Your second and third, etc., these are usually weak, okay? It's a lot easier to get rid of the first one than it is any of the others, okay? So, one important thing to note is that the first proton is usually the most important. Also, if you have a solution that is less than 1 molar, okay, you need to consider both dissociations, all right? I would say the key takeaways from polyprotic acids are that they have more than one proton they can give. The first one is usually strong. The second, and so on, the second, third, fourth, they are usually weak. Examples of polyprotic acids are things like sulfuric acid, or we have like phosphoric acid, which was H3PO4, right? This has 3, right? So you'd have H3PO4 dissociating into H2PO4 minus plus H plus, right? Where it loses 1. Then you have H2PO4 minus, okay? Because this one's already lost 1. So then it's now going to form an equilibrium where you have HPO4 2 minus, and this is plus a proton, okay? And then you take this one and put it there, then you take this one, so now you have HPO4 2 minus, and it's going to form an equilibrium where you have PO4 3 minus plus H plus, okay? This Ka, or this Ka is going to be really, really big. This one is going to be, so this one's going to be greater than 0. This Ka is going to be less than 0, right? Because it's a weak acid. And then this one is going to be much, much less than 0, okay? Because it is a very weak acid, all right? In fact, this usually acts as a base because it's going to take up a bunch of protons, okay? That's the idea of polyprotic acids, okay? All right, now, on slide 34, memorize this list of polyprotic acids. Right, it will be useful. Right, and I would practice going through each of the steps like I did, right? Because our first dissociation is going to have a Ka, then our second one is going to have another Ka, and then our third one is going to have a different Ka, and so on. In that table, they have all those Kas. I'm not asking you to memorize the Kas. I will give that part to you. But I am asking you to know the name of the acid and its chemical formula. All right? Now, the next thing that I want to talk about is on slide 35. Right, how are we on time? Actually, before we go on to slide 35, I think since that's starting kind of a new topic, I'm going to stop here and then we'll continue with what we're going to talk about on slide 35 in the next video.